Hi, and welcome back to Basic Logic, an Open Introduction. In this video series, we're working through many of the chapters in For All X, the Lorain County remix. That's a free and open source textbook you can download on the internet right now. We've already worked through chapters 1, 2, and 3, as well as 6 and 7. Now we're on to chapter 8, Proofs in Sentential Logic. A proof system is going to be different from the truth table system we've deployed already. With truth tables, we can prove that certain sentences and sets of sentences in SL have certain properties. For example, we can see if an argument is valid or if a sentence is a tautology. This was a bit of a semantic system because what we did is we looked at the truth tables directly to find out whether or not a property was there. Typically what we would do is look underneath the column of the main logical operator and see, for example, if it was all T's, which would mean it's a tautology, or whether or not there was a row where all the premises were true and the conclusion false. Now, in this new system of proof, we're going to be proceeding on a syntactic basis. We're going to be directly manipulating and transforming strings of sentential logic. The advantage here is that it'll give us greater flexibility and power. We'll be still able to test for various semantic properties. However, because it's going to require more creativity and intuition, we're also going to be able to do more interesting things. Whereas the truth tables are, in a way, they're mechanical. Once you understand the procedure, you can just kind of by rote go through it. Now, this proof system that we're going to introduce is going to be pretty different. It's going to require leaps of intuition, creativity, and logic. So it's more scalable. One of the great advantages of this proof system is that you're going to be able to test for properties of much larger and more complicated arguments without having to do truth tables with 64, 128 rows. But it comes at a cost. It's not going to be mechanical. It's not just working out the consequences of certain forced moves. So, enough prelude. Let's get right to it. The basic idea behind a syntactic approach to proof and property testing in our new system of derivations is that sentences can be substituted for each other without affecting truth value. That's the basic idea. Now, this sounds like we're going to be leveraging logical equivalence. You're right if you were thinking that. Logical equivalence allows us to interchange sentences, and that's part of what we're going to do. So we're going to be substituting sentences for each other when they're logically equivalent, according to certain rules that I'm going to give you. These rules can be proven, but mostly you're just going to memorize them. Think of it as, a game of some kind. There are certain rules, and if you play the game right, you can meet your objectives. But we're not only going to be substituting logically equivalent sentences. We're also going to break down sentences into its component parts and reassemble them according to rules. How are we going to be able to do that? Well, generally what we're going to be doing in our proof system is we're going to assume that some set of sentences are true and find out what the consequences of that are. Now, for example, if I have a sentence like P and Q, I know that P is true and Q is true if the sentence as a whole is true. So using these techniques, substitution and breaking down, we can determine whether an argument is valid if a sentence has some property. For example, what I mean here is that if an argument is valid, I should be able to build the conclusion from the premises using our manipulation rules, the rules that let us break down sentences into component parts or substitute them with logical equivalence. So it's going to be a bit more creative, a bit more open, and frankly, for me, a lot more fun. So, how do substitution instances work? Well, let's use metavariables again. We're going to use them to represent more complex strings. So, this is an idea we should be familiar with. Take the familiar schema, if P then Q, P therefore Q. Now, we know that's a valid argument. There's no way we can have true premises and a false conclusion. But if P then Q, P therefore Q can also stand in for any case where what we have is a conditional, the antecedent of that conditional, and then the consequent as a conclusion. Let's look at this example over here. What we have is roughly that same schema. If either G or H, then either I or J. We have either G or H, which is the P here. We have the antecedent. So if this, then that. We have this. Therefore, that. This is important because quite generally, any argument with the form if P then Q, P therefore Q is going to be valid, no matter how complex the atomic sentences that the metavariables represent. Let me say that again because it's very crucial. Every argument of the form if P then Q, P therefore Q is going to be valid. as long as the main logical operator is going to be that if, and that you have the antecedent as a separate premise. So it doesn't matter how complicated things are, as long as we can substitute them. The sentential connectives, apart from the negation, are binary. So all we need to do is specify rules for each connective. And that will allow us to manipulate our arbitrary long sentences of SL without having to make huge truth tables. Remember, the truth tables grow literally exponentially. If I have 4 atomic sentences, that's 2 to the 4 rows. That's a lot of rows. If I have 5, 6, 7, how on earth am I going to prove properties of complex arguments? While using the derivation system and substitution instances and specifying rules for each binary connective, we should be able to do that. Again, metavariables are key here, because any argument of the form if P then Q, P, no matter what P and Q are, will remain valid. So if I just specify rules for each connective, we should be able to make a lot of progress this way. So, consider the 2 arguments above. We're going to call them, they have technical names. The first one is disjunctive syllogism. The second one is conditional elimination. In both the arguments above, the basic underlying logical form is always valid, no matter the complexity that might be masked by the use of the metavariables. All we have to do is assume the premises are true, which is the point of an argument. If the premises are true, the conclusion will be also true. It's impossible to have true premises and a false conclusion. So when we're using a derivation system, typically what's going to happen is that we're going to have a set of premises that we're going to assign the value true to, which means that the main logical operator has property T. And from these assumptions or premises, we should be able to derive further sentences. And every sentence that can be further derived from the premise could be the conclusion or a conclusion. Sometimes we're going to have a target sentence. And if we can build that target sentence from the premises using substitutions and breakdowns, then you'll know that that conclusion must follow, must be entailed. So we're going to treat the basic valid forms of arguments as rules we can apply to premises. Sets of sentences assumed to be true, right? So our system of rules will allow us to explore the consequence of having basic argument schemas that are valid. So let's look at disjunctive syllogism. Here are 2 instances of the same thing. On the left-hand side, you have the simple case, either P or Q, not P, therefore Q. On the right-hand side, you have this much more complicated case. Premise 1 is this very complicated disjunction. Premise 2 is the negation of one of the disjuncts. And the conclusion is over here, we see that it's the other disjunct. So it's either one or the other. Now they're very long, but that doesn't matter. It is not the case that it's this one, therefore it's the other. Now I've underlined the main logical operator. The important thing to remember is that the argument on the right-hand side has the same logical form as the one on the left. The second premise is the negation of the first disjunct, and we conclude that the second disjunct must be true. So substitution instances like this apply to any complex sentence. Sentences of SL, since they're recursively generated, can always get larger, but they're fundamentally binary or negated. So they'll exhibit a finite variety of logical form. So what I want you to do is kind of really realize that no matter how complicated a sentence gets, there's always going to be a main logical operator, and there's only going to be a few basic logical forms. At the end of the day, all sentences are going to be of a few basic types, no matter how complex they are. If P, then Q is one of those basic types. Now, P could be this very large thing, and Q could be this very large thing, but the main logical operator is always going to be the if in this case. So there are finite amounts of basic logical forms, even though there are infinitely many sentences. So if we can specify how to work with each basic logical form, we've in fact specified how we're going to deal with every single of the infinitely many sentences of SL. And now the lights have gone out. They're back on. So let's get more comfortable with this idea. Open Chapter 8, Section 1, and look at the exercises in A through H. Go have a look. I'm not going to do this one with you because there's a lot of content here, so it's important. Go look at those problems. Go open for all X, the Lorain For all X Lorain County. Did I just write country? There we go. Let's download the text. Full text as a PDF. See, isn't this great? Let's go all the way to chapter 8. Wonderful textbook. Right, substitution instances and proofs, 8.1. So go have a look at exercises for this chapter here. There they are. For each problem, a sentence form is given. In the meta variables, identify which of the sentences are legitimate substitution instances of that form. So go have a look. Go have a look at these problems. Right? Here we have A and B. So what of the following sentences have the form A and B? P or Q? No. If A, then B and C? Yes, because the main logical operator is an A conjoining two things. No. No. Sorry, this is actually two. This is the same one. Yes. This one is yes. Yes. No. Right? So go through these problems. All right. Okay. So, as I've been saying, there are infinitely many sentences of SL, but there are only a few different logical forms that can be, right? So that's why the recursive set of sentences were finite. So they kind of tell you there's only going to be finite logical forms using metavariables, even though there are many infinitely sentences. These will correspond to the four basic binary connectives and their respective negations. So all possible sentences of SL are some variation on these. And a handful of rules will suffice to handle these forms. In fact, I'm going to introduce some more than, strictly speaking, we need just to keep things easy. But if I have rules for manipulating the syntax of each of these sentences, then we can have a very powerful system that will ignore how many atomic sentences there are. So you'll never have to deal with a truth table of 256, 512, 1024. You don't need to worry about making these giant truth tables. You can manipulate the syntax directly. Right? That's really cool. So all sentences of SL have one of these 8 basic forms. Okay. And why did this go over here? All right. Here are the basic forms again. In fact, no, I had P and not P there because, of course, I guess it's a basic form. It should just be an atomic sentence and its negation. Okay. So stop and think about whether anything follows directly from the assumption that the sentence is true. Because in our derivation system, we're going to be mostly looking at arguments. And in our arguments, the idea is that we're going to assume the premises are true and find out whether or not there are any implications or downstream consequences from that assumption. So let's look at the 8 basic forms. C, assign them true to the main logical operator. Is there anything else we can deduce from there? This is something we've already done with the shortened truth table, so it should be pretty easy. Now we're just going to try and do it more systematically. For example, on the first one, assuming P and Q is true gives you P being true and Q being true. So I know the values of P and Q on the basis of the main logical operator and being true. Now P and Q are metavariables. It hasn't told me anything else about what P and Q as metavariables might represent. It might be a more complex sentence. If it is a more complex sentence, the fact that that sub-sentence is true might iterate into more consequences for what that sentence actually is. By contrast, P or Q doesn't tell me much if the or is true. So go through and see what consequences you can derive from the assumption that these basic sentence forms are true. How was that? Did you pause the video and do it? Did you? Okay. So why don't we do a couple of these? So I've already, let's just open up here. So we have P, this one's not writing. If we assume that P and Q is true, I have a lot of useful information. If I assume that P or Q is true, I don't have a lot of useful information. So that's when I'm going to have to, whatever rule I specify here is going to have to take into account the fact that I don't have a lot of information. However, there's an interesting kind of converse here that if I negate this, and this is true, that means that I know that this is going to be false, but if this is false, I actually don't have a lot of information here, because I don't know what the values of these could be. Just solely on the basis of the information here. But notice that if I negate the disjunction, and I know that this is true, then this is false, then I actually have a lot of information about P and Q. Right? So if you kind of go systematically through these, you'll find that some of them give you a lot of information and some don't. But that doesn't matter because we can still find a way to specify useful rules on the basis of the information we're given. Likewise, if I have if P then Q, and that's true, I actually don't have a lot of information here, but the negation is actually pretty useful. Because if this is true, then this is false, so this actually does give me a lot of information. All right, so have you worked on all these? Good. Let's actually move on, because in order to get to the actual natural derivation system, we'll have to just kind of keep moving. Am I having a bad hair day? So, the basic idea of our natural deduction system, again, is that we're going to start with a set of premises, assumptions, if you will, that are assumed to be true, which means that their main logical operator is assigned T. Then we're going to work out the consequences of this assumption. We're going to find out whether or not some other sentence is entailed by the premises, which would mean that an argument with the premises and that entailment as the conclusion is a valid argument. We can also find out whether some sentence is a tautology or a contradiction. To do this, what we're going to do is apply a set of rules that I'm going to give you. These rules are going to be roughly modeled on the logical implications here that we've already seen. Now, every sentence in SL is some variation of these basic logical forms. The truth of some of these logical forms has interesting consequences. So if I give you rules on the basis of these basic logical forms, you'll be able to disassemble and reassemble and substitute any of the sentences of SL, any of the infinitely many sentences, because they're all going to conform to one of these 8 basic types. The 4 connectives, their negations, and I guess the atomic sentence negation. So the rules of the derivation system, which are going to be based on the basic forms of SL, are going to allow us to create all these sentences that are entailed by a premise. It's also going to allow us to create every tautology and to determine whether a sentence is a contradiction or not, because its negation will be a tautology and we can create the tautology. Okay, so here's an intuitive example of what we mean. So let's work through it. We have premise 1, premise 2, and a conclusion. Is that argument valid? First of all, we're going to assume that the premises are true. So if we work through it intuitively, it's pretty straightforward, then all we need is kind of a notation system that makes our intuitive reasoning clear, justified, and rigorous. Well, if the first premise is true, L and W, then we know that L is true, and we know that W is true. However, if L is true, not F is going to be true, because if L is true, then not F. How do we know that the conclusion W and not F follows? Well, I know that W is true because it's an AND statement on the first premise. I know that not F is true because I know L is true, and if L, then not F. So therefore, I know the conjunction is true. W and not F must both be true given our premises. So we can reason our way to the conclusion. The reason we call it a natural deduction system is because it will mirror this kind of reasoning, right? But it will present it with somewhat more rigor. So let me actually kind of show you maybe how this would work, just as a quick example. And then I'll start giving you a more formal presentation. But I'm always an advocate of just kind of doing first and explaining after. It's a sound pedagogical method. So what is our argument? We have L and W. If L, then not the case that F. And the conclusion I want is W and not F. I'm just going to write my conclusion up here. So my goal when I'm trying to, so I'm going to put the premises here, I'm going to separate them with a line, and now my goal is to create this conclusion sentence on the basis of my premise sentences. What does that mean by create? Well, I talked a little bit about how these logical forms, if we assume the premises are true, they're kind of logical consequences about their subcomponents. For example, a logical consequence of the premise 1 being true is that if L and W is true, L is true. And also W is true. So both of these things have to be true. Premise 1 is true. How do I know it? What I might want to do is say, oh, this is in reference to line 1. So I'm kind of commenting my code, as it were. In reference to line 1, it's an AND statement. An AND statement means both sides are true, so I know that L must be true. Same thing here. In reference to line 1, which is an AND statement, W must be true. Fine. So now I know that if this is true, 3 is true and 4 is true. I also know that not F is true. Why? Because if L, then not F. So that's in reference to lines 2 and 3. And it's a conditional. Right? Because I know for a fact that the basic schema, if P then Q, P therefore Q, is always going to work. And that's basically the schema I have. Right? If P then Q, P therefore Q over here. So I know that all these things are true. All these things follow from the premises. So line 6, I'm done. I'm actually going to write my conclusion that I wanted, W and not F. So I can construct the conclusion from the consequences of the premises. Why am I allowed to construct this? Well, a conjunction is true if both sides of what it connects are true. And I know this is true, I know this is true, so this must also be true, because I've combined lines 4 and 5 into an AND. So that's what it's going to kind of look like. I'm sorry, my handwriting is terrible. But roughly what we're going to be doing is taking the premises, assuming they're true, applying transformation rules and substitution instances, and then disassembling and reassembling the things we know are true to establish a conclusion. And it's going to more mirror a natural line of reasoning. So, what's going to basically happen is that each connective is going to have two rules. An introduction rule, which will introduce a new connective based on what we have, and an elimination rule, which will eliminate a connective. Now, in the example I just did on the board, there was both. First, I eliminated the AND, because I had L and W. So if L and W is true as a sentence, each component must be true, so I can eliminate the AND. Then I introduced an AND later, because I had two sentences I had, and then I can combine any two true sentences into a true AND. So, let's look at another example. Suppose I have premise 1, which is E, whatever E is, and 2F. So, if E is true and F is true, then the statement E and F must be true. And we're going to call that conjunction introduction, because we're introducing an AND. And I'm going to refer to lines 1 and 2 as justification. So if somebody asks, I'm looking at line 3 there. How on earth did you get E and F from? I'm like, oh, well, I had E and I had F already, so I just combined them into E and F because I knew they were already true. So the derivation system is going to introduce, for each connective, an introduction and elimination rule. And then after that, once we have those, I'm going to introduce some extra rules, mostly to facilitate the process of natural deduction. But the fact is, using just the basic intro and elimination rules, we'll be able to do everything we want to do. It's just to help us out. So, remember, a conjunction is only true when both conjuncts are true. So the intro and elimination rules here are going to be really simple. Any two true sentences can be joined, and any two conjuncts can be separated. So intro and elimination for conjunction is really easy. Any two true things can be made into a true and statement. Any true and statement can be broken down into the two things it's conjoining. Now this again is going to be true no matter how complex the and statement is, as long as the and is the main logical operator. The main logical operator and could be conjoining very long sentences, but it doesn't matter if it's like P or Q and Q or S, because I could just break down the P or Q on the one side. That's conjunction elimination, because the elimination rule is about the main logical operator. It doesn't matter how complicated the things it's actually connecting are. So, here's this argument again, what it's going to look like. Because I'm going to introduce conditional elimination more formally now. So if I have a conditional, when can I use conditional elimination? I'm going to need two things. Conjunction was easy. You only need, right, conjunction elimination was easy. For any conjunction, you could just break it down to its component conjuncts. You don't have to break it down. That's up to you to decide whether or not you need the individual pieces. It's a bit like Lego or some other game like that. You get to kind of make decisions about what you're going to break down on each subsequent line. So conditional elimination works as follows. For any conditional, if you have the antecedent of that conditional, you can eliminate the conditional and grab the consequent. So if I have if P then Q and P, I can always get Q, and you can decide when to do that. So the game of the natural derivation looks a bit like this. You are given some Lego blocks, some premises, and at each new line, so if I have 2 lines of premises, line 3 is your move, player 1, and at line 3, you're going to decide to make a move. What move are you going to make? Well, you have to cast conjunction elimination, and then, I don't know why I'm trying to make this more exciting than it is, and then you cast conjunction elimination, and success! You've broken the conjunction at line 1 into one of its component pieces. What is your next move? All right, so if you have premises 1 and 2 here, L and W, if L then not F, right, I just did this on the board, but it's going to look like this, so I'm going to go conjunction elimination, so I've eliminated the conjunction, I've eliminated the and on line 1, and I've gotten L. Then I got W through the same process. Then I get not F. Whoa, how did I get not F? Conditional elimination. Why? I have if L, then not F, and I have L from here. So some of this requires a little bit of creativity and forethought. So you're going to have to know that if you see the conditional, one of your goals might be to create the antecedent to that conditional, because you don't have it yet. You might want to skip directly to not F without line 3 there, but you can't, because you haven't actually demonstrated L yet. So a lot of students want to skip ahead because they feel things are obvious. They're like, oh, obviously L is true because I have the conjunction. So you can't skip any steps. In order to use conditional elimination, you need to have the antecedent exactly as it is in the conditional. So you need to go get that L over here in order to get the not F using conditional elimination. So I get the L, that means I can get the not F. I have the W. If I have W and not F, I can conjoin them over here. So success. The premises entail the conclusion because I could build it from the premises using the rules we have. Therefore, the argument is valid. An argument will be valid if and only if I can construct the conclusion from the premises using the introduction and elimination rules that I will be giving you. All right. So conditional introduction. Now, I said there's an introduction and an elimination rule for each of the connectives. That's true. But conditional introduction is a little complicated, so we're going to press pause on that. And we're just going to move on to some of the simpler ones, such as disjunction introduction, which is really easy. It's a little weird, though. Roughly what disjunction introduction says is that for any true sentence of SL, you can always introduce a disjunct at any time. Now, why is that? I know in real life we'll never use this rule because of the kind of pragmatic rules of discourse I talked about a video ago. Right, always give the strongest relevant information you know. But in logic, if I know something is true, I know that if I introduce either that's true or it's still itself going to be true. So I can say this is a logic video. So either this is a logic video or the Cleveland Cavaliers will win the Stanley Cup. Well, the second sentence is also true because I know that at least one side of the disjunct is true, but it's kind of bizarre. Nevertheless, it's a true and real and sometimes very useful rule that if I have, for any arbitrary sentence P, I know that that if I know if it's true, the sentence either P or Z, whatever Z is, will also be true. And that's going to be disjunction introduction. Right? Because again, we're interested in the consequences of true statements. Now, if you look back, disjunction introduction really is piggybacking off the fact that the or is easy to make true. There's only one case where the or is false. So if I know for any given sentence I know is true, I can just add a disjunct to it, as long as I know it's true. So for any premise, I can just build that premise or something I made up. And that's actually pretty useful. So here's disjunction elimination. So for any disjunction, either P or Q, if I have the further information, not P, then I can give you Q. Or it can go the other way, right? If I have P or Q, not Q, I can get P. Again, so I need two pieces of information here. if I have a disjunction and I know that one side is false, I can give you the other side. So that's the disjunction elimination rule. Now, all these rules can be used when in your derivation. So if I'm online, I've done my premises, and now it's my turn to make a move. I have this like repository of rules I can use. Can I use conjunction elimination? Can I use conjunction introduction? Can I use disjunction introduction? That's up to you. And it will depend on why you're doing the derivation. Now, typically, we're going to be doing derivations to find out whether or not an argument is valid. So it will depend on what you're trying to do. Okay. Let's also bring in another rule, biconditional elimination. If I have if P, then P, if and only if Q, and I have P, then I can get Q. Likewise, if for any statement of the general logical form, P, if and only if Q, if I have the Q, I can get the P. So sometimes you need two pieces of information to get the elimination rule happening. Okay. So again, these are things you're going to have to kind of memorize. All the rules so far have been pretty easy. We directly introduce or eliminate operators if certain conditions are met. Using these rules, we can then derive or create new sentences. And if we can create a new sentence using these rules, then that sentence is entailed by the premise. And by entailed, I mean could be the conclusion of a valid argument. So we already have an example of how this would work and to prove that an argument is valid. If we could construct the conclusion from the premises using these rules, the argument is valid. Now, I did say there would be an introduction and elimination rule for each operator. That's right. But these are going to require slightly more complicated rules, and these are going to be kind of conditional rules, and I'm going to kind of explain what that means. For now, here's a summary of all the rules we have so far. Let's just go over them one by one, and then there'll be an exercise, and that'll be the end of this video. So P, if I have P and Q, you can always get P or you can get Q. That's conditional elimination, conjunction elimination. If I have two sentences, for any two sentences I know are true, I can give you an AND statement. For any P and any Q, I can give you P and Q. Disjunction elimination, for any disjunction P or Q, if I have the negation of one or the other, I can give you the other. For any true statement, I could just introduce a disjunction anytime. It's great. Just add in a disjunction. No cost, no mana, no magic point cost. Just like introduce disjunction for free. Conditional elimination, if P then Q, P therefore Q. So if I have a conditional and the antecedent, I can give you the consequent. And for any biconditional, if I have one side of the biconditional, I can give you the other. So those are the basic, the simple rules of introduction and elimination that we have. So what you should do now is go to chapter 8.2 in For All X, the Lorain County remix. I'm not sure the pagination might be right. I think it changed in the last version. So go look at parts A, C, and E and complete the derivations, fill in the missing parts of the proof until you've really mastered the introduction and elimination rules that we have so far. All right. Thanks for watching.